Hey class, Mr. Hofstad here with a fun lesson, Unit 6, Lesson 6. We're going to look at wave reflection and interference, both important parts of mechanical waves. So our first look into this is with the different types of wave reflection. And these are important. They're kind of easy to forget about or to discount as not being super important, but trust me, they are. And I'll talk you through why these waves are acting the way they do, and hopefully that helps you to remember. So first one, we have a fixed end. So let's imagine this is a slinky and it's fixed at one end, maybe to the wall. As I send my incident pulse through my slinky, the slinky is going to physically move up, and this wave is going to travel through, like you can see in that last YouTube video I posted, and it's going to hit the wall, right? And at the fixed end, there won't be any possibility of the slinky moving up or down. So the wave can't continue through the wall, right? It's actually fixed. There's no more oscillation there. And instead, it travels back, reflected in an inverted way. So why are we getting this inversion? I'll try my best to explain it. So if you imagine this wave front of the sprinky wave pulse reaching the fixed end, there's going to be some force up. And as that slinky is trying to move up, the fixed end is going to apply an equal and opposite reaction force, Newton's third law, down on the slinky. So as the slinky isn't able to move up as that wave pulse reaches the fixed end, and it wants to, that force that's directed up is going to be counteracted by a downwards force at the fixed end of the wall. So the fixed end will actually apply a downwards force, and that downwards force is going to start our reflected pulse back in the other direction, but now our wave pulse will be inverted, flipped upside down, because that starting force, rather than being a force up, right, a flip up of the spring, is actually a force or a flip down, and that is going to propagate and travel as a reflected pulse, inverted. All right, hopefully that makes sense. So you'll always have an inverted but otherwise identical wave pulse at a fixed end, right? So it's important to remember that it flips over because of our Newton's third law happening at that fixed end, that opposite and equal force. All right, our other type of wave reflection is a free end. So we don't have a fixed end or a fixed point. Instead, we have some frictionless loop that's able to perfectly slide up and slide back down. So as our incident pulse of the slinky approaches, right, it's actually going to be able to rise up as that wave front here comes through and into contact with that free end. So this free end is going to travel up and then back down as this pulse comes up and back down. And at this free end, where there's no friction and it's just sliding up and down, we're actually restarting our source vibration. So this traveling up and down is going to be essentially the same initial vertical transverse motion, vibration up and down, that sent this incident pulse traveling to the right in the first place. So it's going to come up, come back down. That's a new vibration, new oscillation up and down, and it's going to trigger a reflected pulse back in the opposite direction, right? So as this comes up and down, we have a new source vibration that's going to send a wave back in the opposite direction, but this is no longer inverted. It comes back upright. So fixed end will be reflected because of Newton's third law. Here we have no forces, right? We just have this new creation of a wave because of this oscillation up and down, and it'll come back upright. So that is important. It is just a little brief thing that we throw in, but it will come up again. So I encourage you to try your best to remember our fixed end, Newton's third law. Our free end is a second source vibration in the opposite direction, but still upright. So how can we apply this to the real world? One big way is through echolocation. So that's a huge real world application. We use it in technology. Bats use it. Hopefully we know what echolocation is, right? It's bouncing sound off an object, hearing it, and determining how far away that object is as a result. So a wave is a wave, usually sound wave. Doesn't have to be. Actually, I think for echolocation it does. But you can use light waves or different radio waves in similar ways. Sent from a transmitter, bounce off an intended target, and reflects back or echoes back to the receiver. To show how we can figure out this distance, right? Let's go through an example together. So it takes 5 seconds for a wave to travel from a transmitter to an object and back again. So that's our transmitter, that's our receiver, and that's our object. If we're looking for the distance to the object, the distance that the sound wave is traveling is actually going there and back. The distance we're interested in is the one-way distance. So that's going to be the most important thing to remember when working with these there and back type questions like echolocation. So if it takes 5 seconds for it to travel there and back, that's important to remember, there and back. So we're actually going there and back in 5 seconds. They're telling us the speed of the sound of this wave is 340 meters per second. We want to determine the distance. It is away. So probably the easiest way to go about this is to recognize that it takes half the time to get to the object. The one-way distance is reached in half the time. So it takes half the time to go one way because the sound isn't slowing down. It's a constant 340 meters per second there and back. So it takes half the time to go our one-way distance, which is what we're looking for. So the time for one-way is 2.5 seconds. Now we're going to use our speed equation to solve for distance. Distance is speed times time. 340 meters per second for not 5 seconds, but 2.5 seconds gives us 850 meters away. So these will be easy to forget our one-way distance, and you really have to look at the wording of the question. We want to determine this distance, right, or how far away the object is from both the transmitter and the receiver, because these for echolocation will always be lined up, same distance. They'll often be just centimeters or less apart. And to find that distance, we can't use the full time because that's going to give us, right, the distance times 2. So we need to remember that we're using half the time because we're only worried about the one-way distance, not the distance there and back. All right, moving on. This is an important part of waves, this idea of how traveling from one medium to another affects our wave. So as a wave goes from one medium to another, if we remember from last lesson, we're going to have a change in speed. Every time you're changing from one medium to another, there is going to be a change in speed. That's just inevitable, right? And it has to do with the density of the molecules, how thick isn't one way to think about it, or how fast or slow that medium is, right? We could think about water being a thicker medium than air, so sound or any wave will travel slower through water than it will through air, which is a faster medium, right? And as it goes from air to water, right, from fast to slow, we're going to have a change in speed as it enters the water. So it'll experience also a combination of reflection and transmission. So two new words here. This idea of some of the energy being reflected, some of it being transmitted. So let's take a look at what might occur. So this is our incident pulse through a fast medium. It's going to travel, it's going to hit this slower medium, this thicker line, and part of it's going to be reflected back. So the reflected back part wasn't free to oscillate up and down without friction, right? It wasn't our free end reflection scenario. It's actually a fixed end at this transition between mediums. So we have a fixed end reflection, which means, right, there was a force trying to act up on this. It resisted and applied an equal and opposite force down and sent a wave back that was inverted. But since some of it was reflected, some of it was transmitted, we're going to have a smaller amplitude, right? That's our full energy, full amplitude. This one is going to be less. Might be half, might be something other than half. I'll just, for simplicity's sake, call it half of that energy, half of that amplitude. All right, so that's the reflected part of our wave, right? And it was reflected like on a fixed end. We're also going to have a transmitted into the slower medium. So this pulse will continue through the slow medium, let's call it water. It'll have, again, a smaller amplitude, but it won't be inverted because it hasn't actually reflected. It's going to continue through with less energy. And one other really important thing, whenever we change from one medium to another, we change our speed. So if this was a fast medium, this was slow, we actually have a smaller or a slower speed in this, let's call it water. So let's kind of take a look at all of the parts of these waves. The reflected part is acting like a fixed end rather than a free end. So as a result of that, it will be inverted. But since it's in the same medium as our incident pulse, it will have the same speed. Since it has the same incident frequency, the same starting frequency, right? Frequency will always stay the same. So we have the same speed, the same frequency, the same wavelength. I don't have my Greek symbol for wavelength. All right, so same V, F, and wavelength as it's in the same medium, and frequency always stays the same. It's now traveling in the opposite direction, right? It's coming back at us this way. Sorry, I'll make that blue. And we have a decrease in amplitude. Because the energy of this initial wave is being split between the reflected and the transmitted wave. All right. Now let's look at our transmitted part. We know always it'll have the same frequency, right? That's a good place to start. Doesn't matter if we change mediums, we're going to have the same frequency as our source. Going from fast to slow means we need to have a change in speed. And since it's now in the slower medium, it's going to have a slower speed. So the speed decreases. And if we look at our wave equation, the universal wave equation, speed is frequency, which stays the same, times wavelength. If our speed slows down, and speed is directly proportional to wavelength, that actually means that our wavelength needs to decrease because frequency is staying the same. So you'll usually see that is connected if speed changes, we'll have to have a change in wavelength as well. Whereas when speed stays the same, wavelength stayed the same as well. We also have this smaller amplitude, so it decreases because we're splitting that energy, but it's upright. It hasn't been inverted because there was no fixed end reflection. All right, so these are tricky, I won't lie, and you can also switch it going from slow to fast. If you're going from slow to fast, more likely than not, you won't have any or as much reflected because it's going to want to vibrate and go through. Maybe I'll go through that homework question with you as well in this video. All right, so that was our wave reflection component. Now wave interference. So interference is really important with waves. Waves can pass right through each other, but when they do occupy the same position, they interfere with each other. So this interference is what we're going to focus on here. So mechanical waves anyways are manipulating the medium they're in, right? They're moving particles around. So even though they can pass through each other, they're still going to have an impact on each other and interfere with one another. So they can occupy the same position. They can superpose, both exist at the same point, but they are actually going to interfere and affect one another. So when they are superposing one on top of the other, we have to work with the principle of superposition, one on top of the other. The resultant displacement of a particle is equal to the sum of its separate displacements. So resultant displacement is equal to the sum of all of the separate displacements, or the separate waves that are superposing, overlapping with one another. And just like displacement is a vector, we need to have our positive and negative displacements with these pulses. So they can actually subtract from each other. So the resultant, we need to include signs for. So there's two types of interference: constructive, when they both have the same sign, when they're either both positive or both negative, we'll have an increase in amplitude. That's why it's constructive. We're making more amplitude, right? It's going to be a constructive experience for the wave. Whereas destructive interference will have a smaller amplitude. So that's when one is positive, one is negative. They're going to either cancel each other out completely if they're equal, or they'll at least have this destruction of some of the amplitude a little bit smaller. All right, here's the ultimate test of my drawing ability. We'll start off with these two guys here. So I'll just use my highlighter. At this point, the dark line is our only wave present. There's no interference yet. Still no interference. But here we have a positive wave from the dotted wave. So the solid will be wave 1, dotted will be wave 2. And at this point, we have constructive interference. So let's call this a +3 and from wave 1 and +1 from wave 2. We're going to have to go up to +4, right? So often it'll help to actually add in numbers here, 1, 2, 3, 4. So when we're adding our sum of separate displacements, this will be a displacement of 3. This will be displacement of 1. 3 plus 1 comes up to 4. And we're going to stay at 4. Right there still has 3 plus 1. 3 plus 1. We're going to stay here for a while. All of a sudden, we're dropping down to 0 from wave 1. 0 plus 1 from wave 2 gives us 1. And we're going to stay at 1. 1 plus 0 until we get to the end. And that is our constructive interference. Right? We're going to look at every point, if this is thought of maybe as our time axis on the bottom. As time goes by, we're going to add together the displacements and get this resultant wave, this superposition. All right, and with negative, we can use the same, and here we would have -1, -2, so on. So starting off at 0, both wave 1 and wave 2 are at 0. Then we're going to jump up and continue here, because this will be 3 plus 0 for this amount of time until we get here. And now we have 3 minus 1. We have to add this -1, so we're going down to 2. And we're going to continue along there until we have another change. So now we're going from 3 to 0. 0 minus 1. We have -1 at this point. -1 continues until we have 0 plus 0. And we're finishing off at 0. So that highlighted is our net or a resultant displacement. All right, the complicated ones are very complicated. I'm going to struggle with this, so it's okay if you do as well. We're going to start, so this is wave 1, this is wave 2. They're both starting at 0. Here, wave 2 is still 0, so we have all of it from wave 1 up until this point. At this point, this is an important point, it's almost like an inflection point. We have now a combination of wave 2 being positive and wave 1 being negative. So we're going to have negative interference. We're working towards 0 here. I'm not actually going to do all of the math. I'm just going to draw the trend. If you were to do this on your own, right, you could actually add up. So at this point we have +2, and at this point we have -4.5, right? So that would get us somewhere at -2.5, like this, right? And we'll just draw that trend like this until we get to a point where they actually are equal, right? So we have -4 here, +4 here. So that's where we're going to cross over our x-axis. And they're going to cancel each other out. So that's the point where positive and negative are equal. We're at 0. They've canceled each other out. And then we're having a smaller negative than positive for a little while, right? And it's greatly increasing or approaching 0 quite fast. It's going to peak at this point where we have the greatest sum of the two, which is somewhere around here. And at this point, wave 2 becomes 0, so we have all of it coming from wave 1. So again, you would have to go point by point. Right here we have almost -5, +3, right, minus 2.5 from here. Right, we can do that at every point along this x-axis. So here I am -5 plus 4.5, or 3.5 actually. So that would be -1.5, right? And just continue finding these points until we get a good enough trend line to fill them all in. Right, and that's where we line up again. So, yeah, you really do have to count -1, +1, add them together, because we're summing the total displacement at each point to find our resultant displacement. So these are longer questions. You do have to be able to do it. Hopefully this method of counting our positive and our negative at each point, right, along these vertical lines, right, we're adding the displacement. So this would be like our x-axis, our displacement. This would be like our time. So at this point in time, we have all of it from wave 1, 0 from wave 2, plus -4. Here we have, at this point in time, we have, right, -4.5, but +2. So we get -2.5. And we can do that all the way through, adding together our displacements, positive and negative, until we can draw in the resultant displacement and what our superimposed wave would look like. Okay, I did say I wanted to show you our waves. I think it's going from, yes, heavy into fast. So in this case, it's actually a spring going from a heavy spring to a fast light spring. So it's going to travel slow through here, right? And as it reaches the fast, it's going to speed up, first of all, because it's a faster medium. We're not going to have any reflection back, because this isn't really a fixed end. It's actually more of a loose end. So it's going to continue to travel through upright. It'll have the same energy, same amplitude, because there's no reflection, but it will be faster. So speed will